Hi everyone, I'm Yuvraj Suresh Babu, and today my team and I'll be presenting our project on evaluating and improving cache replacement policies using benchmark driven analysis. This work is grounded in the idea from a research paper published at HPCA 2021, where the authors explored using reinforcement learning to design a smarter cache replacement policy. Our focus was to build upon that idea and conduct a comparative analysis using real benchmarks to understand how existing policies perform and where there is a room for improvement. So, caches plays a major role in bridging the speed gap between processors and memory. But whenever a cache is full and a new block needs to be loaded, we need to decide which existing block to evict. This decision is handled by what's called a cache replacement policy. Traditional policies like LRU and SRRIP rely on simple heuristics like recency of accesses or re-reference intervals, but they do not always perform well across different types of workloads. Newer policies like SHIP or Hockey often improve hit rates by using program counter information to track reuse behaviors. However, this comes at a high cost. For example, SHIP adds around 20 kb of overhead for a 2 MB LLC, which is not practical for many real world designs. So, our aim in this project was twofold. First, to evaluate the strengths and limitations of policies like LRU, SRRIP, and RLR, reinforcement learned replacement policy, across diverse range of workloads. And second, to understand how reinforcement learning can help us design better, more adaptable policies with minimum hardware overhead. For all this, we used the ChamSim simulator and SPEC CPU 2017 benchmark. Now that we have seen what cache replacement policies are, let's talk about why they matter so much, especially today. First, performance. Cache misses are expensive. When the processor does not fit data in the cache, it has to go fetch it from the main memory, which can be 100 to 300 cycles slower. This delay adds up. In fact, studies shows that memory stalls can account for nearly half the CPU's idle time in many workloads. So, even small improvements in cache efficiency can result in a significant performance boost across the systems. So think about applications like AI model training, scientific simulations, or even cloud web services. These workloads often have irregular and dynamic access patterns, which means static replacement policies like LRU just can't keep up. They make poor predictions and causes cache trashing. So evicting useful data too early and bringing in data that does not get reused. Second is hardware constraints. For many years, we relied on Moore's law, the idea that transistor counts double every 2 years to improve performance. But now the rate is slowing down. We can't just throw more hardware at the problem. Complex designs are harder to manufacture, cost more, and take longer to verify. That's why policies like SHIP, even though they offer better performance, are rarely adopted in real hardware. So why is this? Because they require propagating the program counter all the way to the last level cache, adding new fields to cache structures, modifying CPU pipelines, and increasing verification complexities. For many chip designers, this added complexity just isn't worth the marginal gain. So there is an urgent need for cost-effective, adaptable cache policies, something that works well without requiring a major redesign. That's where machine learning comes in, and specifically reinforcement learning. The RLR policy we explore in this project learns from the runtime behavior of workloads and make more intelligent eviction decisions without the need of PC information. Finally, looking to the future, smarter cache policies can make our system not only faster but also more energy efficient, especially in multi-core processors, edge devices, and data centers where power and scalability matters a lot. Next, Tamil would take over.
Hello everyone, my name is Tamil. Let's start by understanding the evolution of cache replacement policies and the motivation behind our project. In modern processor, cache replacement policies determine which cache line to evict when new data arrives. An efficient policy helps reduce memory latency and improve system performance. Over the years, several strategies have been proposed, each trying to balance between performance, hardware complexity, and adaptability. First, the traditional policies. The most well-known ones are like least recently used, re-reference interval prediction, or based on simple heuristic like recency or reuse prediction counters. These are easy to implement in hardware and come with lower overhead. For instance, LRU just tracks the order in which cache lines are accessed, while RRIP assigns a small prediction value to each cache line, indicating how likely it is to be reused. However, these static rules have a downside. They often struggle with dynamic and unpredictable workloads, especially in complex multi-core environment. To improve the adaptability, PC-based advancement came next. Policies like SHIP, Hawkeye, or Glider use the program counters, especially the idea of the instruction that accessed memory. To learn reuse behavior, if a certain instruction tends to bring a data that get reused, the policy learns to retain the lines longer. These techniques showed notable performance improvements, often approaching the theoretical optimum known as like a Beldi policy. But this power comes at a price. Using PC at the last level cache means we need to propagate PC information through pipeline across cache levels and even store and index PC signature in new hardware structures. This significantly increased area, power, and design complexity, making these policies difficult to deploy in commercial process. In response, researchers explored counter-based alternatives. These policies introduced eviction counters per cache line. They monitor access frequency, time between hits, or access type to make replacement decisions. While promising in theory, many of these designs still rely on PC signature to maintain predictive accuracy. As a result, they face a similar integration hurdles, and their benefits may not always justify the hardware cost. When it comes to current state of research, in recent years, machine learning has taken center stage in cache replacement research. Rather than handcrafting rules, researchers are training models to learn patterns in cache behavior. Techniques like reinforcement learning, deep neural network, and even imitation learning are being used to build adaptive cache policies. These models learn to predict which data is likely to be reused and which can be safely evicted, helping to dynamically optimize hit rates even in complex and in real world workloads. A big focus of this research is on edge and cloud caching, where access patterns can change rapidly and unpredictably. But it is not just about performance anymore. Today's designs must also consider the security and energy efficiency. For example, cache structures have become a target for side channel attacks, where an attacker infers secrets by observing cache behavior. Machine learning driven policies are being explored to mitigate these attacks by making access and eviction patterns less predictable without sacrificing the performance. At the same time, energy efficiency is now a critical concern, especially for IoT devices, data centers, and multi-core systems with a large shared caches. Researchers are developing machine learning-based policies that are just accurate but also lightweight enough to viable in low-power environments. Still, several gaps remain in the field. First, there is a persistent trade-off between practicality and performance. The most effective policies, those that mimic ability or use deep PC-based tracking, require complex hardware. Simpler policies are easier to implement, but lack in adaptability to evolving workloads. Second, there is a limited research on global cache line hierarchy optimization, coordinating policies across like L1, L2, and LLC. Few existing solutions are truly workload aware. They are not optimized for emerging domains like AI, cloud services, or big data analytics, which have unique memory access patterns and high sensitivity to caching the strategies. That's where our project comes in line. We evaluate four policies: LIU, SRRIP, Hawkeye, and machine learning inspired RLR. Using a ChampSim simulator, our focus is on workload adaptability, how well each policy perform when access pattern shift. By comparing both traditional and ML guided techniques, we aim to identify practical yet powerful policies that can improve real-world cache performance without hardware cost or full PC tracking. When it comes to like reinforcement learning for cache replacement policy, traditional cache replacement policies like LRU rely on heuristics, which don't adapt well to varying program behaviors at runtime. This often leads to suboptimal eviction decisions, especially in workload with irregular or long reuse patterns. Reinforcement learning, on the other hand, enables an agent to learn and adapt dynamically based on actual memory access patterns. In our framework, the agent observes the current cache state, EST, selects an action, which is AT, such as like evicting a particular cache line, and then receives a reward RT plus 1 based on the effectiveness of that action. The agent transition to a new state, which is ST plus 1, and then cycle continues. Over the time, the agent learns which action yield better rewards and develops a cache replacement strategy that is more suited to real-world program behavior than the static policies like LRU. This adaptability is especially valuable for modern and complex workload where static policies often fall short. Further things will be carried forward by teammate.
Hi, I'm Sushil. Let's see what is reinforcement learning framework, it's working, and how we have implemented it in our project for cache replacement. So begin with the input trace, which is using the SPEC 2017 traces. This includes memory access information such as the program counter, access type. A feature extractor processes each access and constructs the current state. This state is passed to the agent, which is implemented as a multi-layer perceptron. It has 334 input features, one hidden layer with 175 neurons using a 10H activation and 16 output neurons, each corresponding to a potential eviction candidate in a 16-way set associative cache. The agent chooses an action using a epsilon grid policy with epsilon set to 0.1. 90% of the time the agent picks the action with the highest predicted Q value, and 10% of the time it chooses randomly. This encourages exploration of alternative actions while mostly exploiting the current policy. So finally, the environment provides a reward R of t based on the outcome, such as whether the evicted line was reused. This closes the feedback loop and allows the agent to update its policy based on real performance. So coming to the feature engineering and state representation, to make smart decision, our agent needs a rich and informative view of the cache state. And this is where we use the feature engineering. We designed a 334 dimensional state vector, which captures three types of information. The first is the access features, such as memory offset and access type. These are auto one-hot encoded to preserve categorical distinctions. And second is the set level information records, like metadata, like the number of access since last miss, giving a sense of local history. Finally, the cache line specific features include line age, hit counters, and reuse prediction flags. So the numerical features are normalized between 0 to 1 to ensure consistency and effective learning. This high dimensional input allows the agent to identify subtle patterns and correlations in access behaviors that the traditional policies simply overlook. By feeding this detailed state into the agent, we empower it to make more context-aware eviction decisions, which improves overall cache performance. So coming to the reward function and training strategy. So if the agent evicts a line that isn't reused for a long time, it receives a positive reward. If it mistakenly evicts a line that's reused soon, it gets a negative reward. In situations where it's unclear, it receives a neutral reward. So this reward structure ensures that the agent aligns its behavior with long-term cache efficiency. So the training strategy that we have used is experience replay. We store every state, action, reward, and next state tuple in a circular buffer. Instead of training on recent transitions alone, we randomly sample batches from this buffer. This breaks temporal correlations, improves generalization, and helps avoid local minima. Experience replay also allows the agent to replay to learn from rare but informative past experiences multiple times, which improves the sample efficiency and accelerating convergence. So the result is a robust data-driven policy that outperforms the static policies like LRU, DRRIP, etc. So coming to the ChamSim integration, we implemented our method as a custom replacement policy, which allows us to control how cache lines are managed. At each cache miss, we capture per line metadata like age counter, hit counters, type registers, and use this to construct a state vector as previously stated in the previous slides. This vector gives us a snapshot of the current cache's current state. So we use the epsilon grid selection strategy to choose victim block for eviction. So finally, we assign a reward based on future reuse. The hit counters go up for successful reuses, while misses lead to an update in our learning process. This feedback loop allows our policies to continuously improve over time by balancing exploitation and exploration effectively. So the next part will be taken over by Karthik and Muralidharan.
So hi guys, my name is Karthik and Muralidharan. So let's go over our evaluation setup in ChamSim using the SPEC 2017 benchmarks, which is a standard for testing CPU performance. We measure two metrics, IPC and MPKI. And for a baseline configuration, the L1 I and D caches are both 32 KB 8-way associative, meaning each cache set can hold 8 lines with 4 cycle latency for quick access. The L2 cache is 256 KB 8-way, but with a 12 cycle latency due to its larger cycle. The last level cache or LLC is 2 MB 16-way with a 20 cycle latency, reflecting its role as a larger but slower backup. We also use a prefetcher. For L1, it's a next line strategy, predicting the next cache line. For L2, it's IP straight, predicting based on instruction patterns. Lastly, a branch status by model, making simple but effective predictions for branch outcomes based on past behavior. So first, let's see our IPC graph. Uh, so starting with Pearl bench, DRR-IP achieves an IPC of 2.718, while RLR and SHIP lead at 2.953 and 2.853 respectively. LRU and random lag at 2.518 and 2.318, showing that advanced policies handle this workload better. In GCC, RLR again excels with 2.376 compared to LRU's 1.889, a significant gap highlighting RLR's adaptability. For Omnitep, all policies struggle. RLR's IPC is just 0.5854, which is slightly better than LRU's 0.3975. This confirms Omnitep's challenging access patterns. Now, if you look at Xalen, DRR-IP and SRR-IP spike to 3.578 and 3.463, while RLR drops to 1.869. This shows static policies can sometimes outperform learning-based ones in specific workloads. Across benchmarks like MCF and XZ, RLR and SHIP consistently lead. RLR hits 3.763 in MCF and 1.871 in XZ, while LRU falls to 3.398 and 1.524. Random is often the lowest, like 1.103 in MCF, showing its inefficiency. Overall, RLR and SHIP frequently outperform others, especially in high IPC workloads, due to their predictive and adaptive nature. LRU and random struggle with dynamic patterns, while DRR-IP and SRR-IP shine in specific cases but lack consistency. This confirms RLR's potential for improving performance across diverse workloads. Now let's see our MPKI graph. So again, starting with Pearl bench, we see high MPKIs. DRIP at 4.248, but random is worst at 4.548. RLR and SHIP perform better at 3.919 and 3.918, showing their ability to reduce misses in this demanding workload. In GCC, RLR again leads with 6.053, while LRU with 9.906. A notable gap showing LRU struggle with dynamic patterns. For Omnitep, MPKs are extremely low, RLR at 0.0049 and LRU at 0.00538, confirming this workload's predictable access patterns as we saw earlier in our IPC graph. Now look at Xalen. RLR and SHIP are best at 10.68 and 11.912, while random jumps to 12.05, highlighting its inefficiency. In benchmarks like MCF, RLR's MPK is 3.532, which is better than LRU's 3.607, and in XZ, RLR achieves 15.71 compared to random's 24.3, which was a significant difference. Across most workloads, RLR and SHIP consistently have lower MPKs, often around 4 to 10, while LRU and random frequently hit 15 or higher, like 24.47 or LRU in NAB. Overall, RLR and SHIP outperform others by adapting to access patterns, reducing misses effectively. LRU and random lag, struggling with diverse workloads, while DRRIP and SRIP fall in the middle, showing that adaptive policies like RLR are better studied and suited for improving cache efficiency. So coming to our conclusion, so we evaluated multiple cache replacement policies in ChamSim for last level caches using SPEC 2017 workloads, which provide realistic and diverse access patterns. We tested traditional policies like LRU, which evicts least recently used cache line, and SRIP, a static policy that predicts how soon a line will be reused based on a fixed interval. Both showed solid performance by handling dynamic access patterns effectively, ensuring stable cache efficiency. However, reinforcement learning based policy outperformed them. This is because it learns from cache hits and misses, adapting to workload changes in real time, unlike LRU and SRRIP, which rely on fixed rules. This adaptability makes it more effective at predicting which lines to keep, reducing misses, and improving overall cache efficiency, showing strong potential for future optimizations. Thank you.